Tomonaga-Oettinger liquids, and let me just wrap up a little bit what I flashed maybe a little bit fast in the last lecture on the disorder. So just to say a little bit more slowly what I said in the rush of the end of the last lecture, that we want to look at disordered bosons. So we take kinetic energy of the particle, some interaction which will be repulsive between the bosons. So far so good. These are the models we looked at, and then we put a random chemical potential which couples to the density of bosons, for example, and which will play a role. And as I was mentioning, this is a problem that bosonization allowed to solve already some time ago in '87. And the competition between disorder and interaction is highly non-trivial. Disorder in 1D leads to localized phase where instead of having plane waves, you get exponentially localized wave function. This is the celebrated Anderson localization, which works for non-interacting particles. And if you put both, you have a remarkable phase diagram where you find that first the repulsion between the particles delocalize, so they transform these localized bosons, which are sort of trapped in the minima of the random potential, into a superfluid. But then if you crank up too much the repulsion between the particles, they relocalize and give you again something where essentially you get an insulating phase. And this phase has been called the Bose glass. And this is directly a consequence of this competition between interaction and disorder. The single particle correlation function, instead of decaying as a power law, like in the Tomonaga-Oettinger liquid, now decays exponentially with a certain characteristic length that people call the localization length. And this is one of the signatures of this localization. So as a result, if you do the Fourier transform of this object, this will be a kind of Lorentzian-like object. So by looking at the width of this Fourier transform, you can decide whether you're in the superfluid phase or in the localized phase. So instead of doing it with true disorder for various technical reasons, people in the cold atoms have mostly used biperiodic potentials. If these two potentials are in, if these two periods here are in an incommensurate ratio, then you can show that what you have is a model which is very close to a true disorder system, and essentially you get a phase diagram which actually is very similar to what you would expect for a true disorder. You have as a function of the repulsion, of course, here, because you get one periodic potential, you're polluted by a Mott phase here, but that's unavoidable. And then you get the transition between the superfluid and the Bose glass phase when you increase the strength of the second coupling, which means instead of having a simple periodic potential, you go to this quasi-periodic potential. And lo and behold, this is something that could be measured in experiments done in the group of Giovanni Modugno and Massimo Inguscio in Florence. And just to flash the same phase diagram that I flashed last time. So now this is the experimental phase diagram, where what is measured is the width of the Fourier transform of the single particle correlation function. This means very narrow, this means very large. So very large is the localized phase, very narrow is the superfluid phase, and you see that globally you have a phase diagram which is in good agreement with what is expected here. Of course, here you see very large, and this measurement alone doesn't allow you to distinguish between the Bose glass and the Mott insulating phase. So this line here is a kind of separation between the two, and you need other experiments to distinguish between the two, but I will not go into these details. Here is an image of the width of the central peak at the temperature of the experiment. The blue curve would be the width of the central peak at 0 temperature. So it tells you that if you want to do a good job with the experiment, you need to take into account a certain number effects. You can also study this by another numerical techniques. I show this here. This is a work we did in collaboration with Epeng Yao when he was doing his PhD with Laurent Sanchez Palencia in Polytechnique. And you can use quantum Monte Carlo, and essentially you can probe the phase diagram of these disordered interacting bosons, and you see that there is a Bose-Glass phase, a superfluid phase. This is essentially the axis here corresponds to the repulsion here. If you want, the more you go there, the more repulsive are the particles, and this vertical axis is the chemical potential of the system. So just to show you that these are problems that are reasonably under control to study now, thanks to the analytical and numerical techniques that we have. Okay, so these were the two first lectures, and as I promised, I want to do in this third lecture the crash. So, because I don't want you going home and saying, 1D is fantastic, everything is understood. Okay, let's work on 3D, because there is nothing for us to do there. So I will show you now only things for which we don't know, which doesn't mean we cannot publish papers. You can always publish a paper, even if you don't have the answer, especially if you don't have the answer, because then you can do wild approximations. Then someone else will say, no, but this is bullshit. My approximation is better than your approximation. Then you can do a comment and a reply and whatever. No, I'm joking. But you have to work on the problem. So working and sending your results to the community, seeing the reactions, having other people who say, they have problem using their DMRG, but with my quantum Monte Carlo, I can do best and whatever. So you work, you publish, you move forward on a problem, but it doesn't mean you understand it. And so I will show you now problems on which we work, we publish, we have results, but we count on you to give the final answer, put the last nail in the coffin of this type of problem. So I called it TLL and the great beyond. It's whatever. Let's go back to disorder and interactions, because I showed you, fantastic, we have the phase diagram, everything is understood. Think again. So without interactions, actually, if you look in one dimension, and now you want to compute the transport. You don't want to get the phase diagram, the thermodynamics, but after all, if you want to distinguish between a superfluid and an insulator, the best is to measure the conductivity of the problem, or the conductance of the problem. And so the idea is, what is the conductivity of these disordered bosons? And actually, without interaction, so for fermions, because non-interacting bosons are a little bit pathological, but let's say for fermions, there is a guy who worked out a full solution of this problem in presence of disorder, and that's the same Berezinski than the one of the Berezinski-Kostelis-Thouless transition, and he did that in the mid-70s, so pretty early. And what Berezinski is telling you is that if you measure the frequency-dependent conductivity, as a function of the frequency, but at zero temperature, then you have a very weird response. You have a response which at low frequencies is omega square. So at omega equals 0, it's 0. You get an insulator. That's the Bose-Glass phase. You're very happy. You get or Anderson insulator. You're localized. And then as the frequency increases, you get some response. And then you have a peak somewhere at a certain frequency, and then it goes down as 1 over omega squared. So this is a very beautiful analytical solution. Believe me, it's highly non-trivial. I mean, if you have 5 minutes, try to see how you could write it. Non-interacting particles, just the particles and the disorder. Good luck. And the peak is omega is the velocity, so the Fermi velocity, let's say, divided by the localization length. So in a way, you can imagine of your system as blobs which are pinned, and then you make them oscillate around their equilibrium position, and there is a kind of frequency which characterizes this oscillation, and the largest is the localization length, the lower is this slushing. But okay, so that's the analytics. The omega square actually was predicted way before Berezinski's solution by Sir Neville Mott, who had an argument a la Neville Mott, which is no calculation, but just, you know, a direct red line with God or whoever as the solution of these problems. But what Mott said, he said, okay, if I look at the absorption of energy of a system, I know that in an electric field, this is sigma, the conductivity, times E square. That's response. Now, how can I absorb? If I send photons with energy h bar omega, I will absorb a photon h bar of energy h bar omega, and the number of transition I can make correspond of the number of states which are distributed between a band of frequencies of order h bar omega. So if now I assume that my disordered system has a density of state which is not too different from the metal, which is probably the case if the disorder is weak, the number of state is the density of state times h bar omega. So I should get omega square. And he was right. So, okay. He got a Nobel Prize. And then there is another guy who was even smarter, with Bert Alprin, who understood why there is the log square here. So if you want to understand why there is a log square, I refer you to Bert Alprin. I won't explain to it, but this has something to do with the overlap of the localized state, which are decreasing exponentially. Okay, anyway, just to tell that for the AC transport, we understand reasonably well what is going on without interactions. So with interactions, there are a certain number of modifications that we can work out from the RG, from the solution that I showed you, the 87 solution with Ein-Schulz. In particular, the localization length is drastically modified by the interactions. Instead of being 1 over the disorder, it has now a power law which is coming from the interactions. But the shape of the response remained roughly the same, except again, at high frequency, instead of omega square here, you get another power. Because you're in a Tomonaga-Luttinger liquid, well, you know, you get powers, and this power will depend on the Luttinger liquid parameter K. So you can compute this relatively well, and at low frequency, you get the same omega square than you were having from Berezinski's solution, essentially. So this is something which we think we understand reasonably well, and more recently, the paper is published. It's published in a EPGD. We did some numerical calculations using DMRG, using the MPS method that you heard of this morning with Shintaro Takayoshi. And we found, indeed, curves which fully confirmed the Berezinski solution. So you could wonder, why am I talking about this in the crash section? Well, the crash, so you can do with interactions, and you see the omega square, you see the power law here, tail, so everything goes well. The crash occurs when you want to discuss the DC transport. The response not at finite frequency, but the steady state. So the simplest one, you put contacts, you have this system, you want to pass a current, and you want to know what is the conductivity of the system as a function of the only parameter which is left at your disposal, namely the temperature. Okay. And there we are having to, we have to face a very severe schizophrenia. Because on one hand, you can do a calculation like the one we did here in this old paper with Thomas Natterman and Pierre Ledoussal, where you write an action based on the bosonization solution. So you start to recognize the kind of Hamiltonian that I wrote. You have the disorder term, which is something like this. which is the cosine, if you want, that I wrote before. This is the random phase coming from the disorder. This is the amplitude of the disorder. And you put an electric field to drive a current. The electric field directly coupled to the phase phi. You can check that this is indeed the right action to write. So if you don't know what to do this afternoon, you have 5 minutes. Try to solve this problem. And if you solve this problem, you will get the current. Okay. You can reduce this to a discrete model if you want to do it. And at the end of the day, I'll skip the solution. When you do this, you find that what you get are solitonic excitations, and you can characterize these solitons. And when you do it, you find that the conductivity as a function of the temperature is exponential of minus 1 over square root of the temperature, with parameters which depend on the Luttinger liquid, on the disorder strength, and so on and so forth. So you find that sigma of t is proportional to exponential of minus, let's say, a square root of 1 over t. So when the temperature goes to 0, this goes to 0, which is what you want in an insulator. Okay. Now, this is a wonderful expression, and it has a name. It's called variable range hopping. And this was invented by Mott, again, way before. And what Mott was saying, he says, you get localized state here. So you should jump from one localized state to another empty localized state. But of course, if you jump too far, the overlap between the wave functions here will be ridiculously low because it's exponentially decreasing. So you don't want to jump too far. But if you jump too close, the probability you find a state which is within a certain distribution of energy of your initial state is much more limited. So you should find the best compromise between jumping far, because then you can find a lot of state with practically the same energy than your initial state, and jumping close, because that's the best thing for your overlap. And Mott said, but you see, I don't conserve energy here. So in order to violate the conservation of energy, I put a bath. So variable range hopping, Mott, you put a bath. And then Mott said, oh, well, my bath can provide with a distribution exponential of beta epsilon r energy. So epsilon r is the difference of energy when you jump. And then I have to worry about the overlap of the wave function, so I get exponential of minus r over psi. So I won't do the derivation, but if you do the derivation, you optimize between these two factors, you will find that the conductivity, sigma of t, is exponential of minus 1 over t to the power d plus 1. That's the result of Mott. D equal 1 makes, 1 over d plus 1. What did I do? Because this would be 2 here. So this is 1 over d plus 1. My mistake. So this is the result of Mott, and you see that this is exactly what we get with our solitonic, very sophisticated solution. So everything seems to be correct. Here you have it here. This is the full expression. He did it for non-interacting particles. So this is something which we have the solution for interacting particles. That's why we get the Luttinger liquid parameter here instead of the density of state of non-interacting fermions and things like this. So you could say we sort of demonstrated the existence of Mott solution. Fine. Now the question is, what should we do if we have no bath? In condensed matter, this is more or less an academic solution. It's a little bit like discussing, how many angels you can put on the tip of a pin, or related very important academic questions of the Middle Ages. because there is always a bath in condensed matter. You get always phonons, vibrations, stuff. But in cold atoms, the systems are remarkably isolated. So people started to ask, but if I have no bath, what is the answer? And there, it's much more complicated. And actually, the traumatic experience is if you take non-interacting fermions, and you recognize that all states are exponentially localized in 1D, which you know this is the exact solution, well, you can compute the conductivity. And then you will find that without a bath, sigma of T is 0 at all temperatures. Because in a way, changing the temperature is like sweeping the chemical potential to higher energy states. And since they are all localized, doesn't conduct. So on one end, you get this answer. On the other end, you get this. This is, of course, for non-interacting. Now you could say, oh, I have an interacting problem, so maybe the system can be its own bath. Because of interactions, this state here can exchange energy with other states, and then instead of having phonons or whatever, it can redistribute its excess energy to the other state. So question, if I have an interacting problem, should I get that or that? Because you see, in this calculation, there is a prefactor which we don't know, which we cannot compute by the solitonic calculation. And this prefactor could go to 0 if the coupling to the bath goes to 0. So this is what I would say a relatively open question, but still something on which there was a lot of progress and a lot of publications. And the fact that essentially one can wonder whether there is the need of the coupling to a thermal bath, or whether, with interactions, the system can be its own thermal bath. In other words, will the system thermalize or not? And with a bath, as I said, you can compute all calculation with RG, which was giving power laws here, and then the variable range hopping results here, and whatever. So you get pretty good response. Again, Mott variable range hopping, as I was mentioning, and you can get your answer. Without a bath, well, that's the question. And some people attack this question very seriously. There are a lot of people, but a seminal paper was a paper by Basco, Alainer, Altschuler, and a practically simultaneous paper by Gorny, Mirlin, and Polyakov. Not the same Polyakov than the one of Polyakov, Belavin, and Zamolodchikov, another Polyakov. And a lot of work by David Hughes. And this went under the name of many-body localization. What I told you before was also many-body localization. This is localization of many-body systems. But what they meant here by many-body localization, so I'll try to distinguish the vocabulary, is localization of particles with interactions in presence of disorder in an isolated system, in a system which has no contact with the outside world, no thermal bath, no thermostat, no whatever. And their answer, and you can find a lot of information in this review of modern physics here by both theorists and experimentalists, is no, if there is no thermostat, the conductivity remains 0 up to the point where a critical temperature is reached. So, in other words, the answer that these people are saying is that if I have no bath, this answer is not valid immediately, but what you get is you get a conductivity sigma of T which will stay exactly 0 till a certain temperature T star, and then we'll go back to the I would say, the usual curve. The curve that we derived, but I draw it that way, but don't take the curve itself seriously. And of course, that's a remarkable result, if true, because it says the system will not thermalize. If you prepare the system in the disordered system, in the disordered case, and you relax it, it will not reach a thermal state of equilibrium. And so there are a lot of studies that people did on this, and showing or trying to show that the system will not be ergodic, such a disordered interacting system will not be ergodic, even if you are at finite energies. I'll talk about energies rather than temperatures. And there was a lot of studies using both numerical techniques, very difficult because you need to do essentially exact diagonalizations to answer this problem, or analytical techniques, very difficult because you need to be able to compute the property of a disordered system at finite temperature in presence of interactions. So technically, you can answer this question by solving the Hamiltonian I showed you before, except it's an Hamiltonian with a big cosine, an ugly cosine in it, and nobody has found a method to give a controlled solution of this Hamiltonian at finite energy. Yep. There is no temperature. You say you work at a given energy for the initial state. So it becomes more an out of equilibrium problem. Let me just, okay, I'll switch you off so that I get some light. Sorry, you're in the dark. Don't you think that my speech is illuminating? No, okay. Well, there was one time a speech. I'm sorry for the non-French, but I cannot resist telling it. There was once a speech of De Gennes in front of Anatole Abraham, and Abraham he had the reputation for being a tough cookie. And at the end of the speech of De Gennes, he said, "Oh, Monsieur De Gennes, vous nous avez éblouis, mais vous ne nous avez pas éclairés." So you blinded us, but you didn't brought light to the problem. So this was a bad joke. Okay, so for example, let me give you a possible way you can decide this. You start from a situation where you put one particle every two sites. This is your initial state. So this state is an excited state. It's not a ground state or whatever. And then you let go. And you wait a long time, and you want to see if the, let's say, the difference of population between the site 0 and the site 1 tends to 0, in which case you would say my system thermalizes. It goes back to a thermal state, because in a thermal state, this energy has been redistributed such that I have equal population on both states. Or if this goes to a constant, then my system doesn't thermalize, and therefore it's still localized at long time, so its conductivity is probably still 0. So this is, because of course people wanted the simplest situation, for example, they started with infinite temperature. So density matrices which are 1, and then trying to compute conductivity in this situation. So this is intrinsically a problem which is out of equilibrium. I have the right to be there. I mentioned out of equilibrium word. That's good. So this is a problem which is out of equilibrium, the question of thermalization. But you can also address this problem in a simpler equilibrium language, which is to say, if I was doing linear response, Kubo formula is sigma of t computed from the Kubo formula, which is an equilibrium correlation function. Is this 0 or non-zero? And there is a huge fight in 1D, in higher than 1D, and so on, to decide whether this is true, this is not true. I certainly won't take party for one camp or the other. What is sure is that the problem is not simple, and the solution which is here, the one we gave here, implicitly assumes a small but finite coupling to a bath. And so if you completely remove this coupling, the prefactor here, this doesn't change. but the prefactor here can well be 0. And then you have to worry about what is the next term in the expression, and this term can perfectly be 0. Again, the non-interacting answer is also mathematically exact. There, the answer is 0. There is no conductivity at any finite temperature for non-interacting particles that are localized. So this problem is known as many-body localization, and this is a problem that has, let's say, started huge fights because it's a very difficult problem, and that both analytical and numerical techniques are essentially really at the edge of what they can do. For example, you could ask us, why didn't you do the Giamarchi calculation here that you showed us here? Well, why didn't you do it at finite temperature? Well, because it's considerably more complicated to do the MRG at finite temperature than to do it at 0 temperature, and because we have to distinguish between an exponentially small quantity and 0. So it's not only imagine we have the result, we have to decide whether the answer is something like this, but this would be exponential of minus 1 over square root of t. So this is, I draw it that way, but I could have drawn it more like this, no? Something like this. So it's very hard to say this is 0 or this is a tail here which is so small that you don't see it. So one needs answer. There are something which is called, which mathematicians call a quasi-proof. You can take your pick. You can say it's either a proof but with very reasonable assumption that has not been proven strictly, which has been given by Imbri. Or you could say there is a flaw in the demonstration, so it's not yet proved. Okay, that's why I'm saying I'm not taking, I'm not telling you what the right answer is. I just want to point out that this is an open problem, and this is a problem on which a lot of people are sweating very hard, and a lot of very, very good people are sweating very hard to give an answer. Technically, one can give it from the bosonized Hamiltonian, except in practice, nobody knows how to compute this bosonized Hamiltonian to extract the conductivity at finite temperature. Okay, so that's one problem, and again, I think it's a beautiful problem because it touches out of equilibrium physics. It touches the question of thermalization of a system. Is a system ergodic? Is a system thermalizing? You know, we kind of implicitly assume that after a while we will thermalize, and that's a difficult question. Just to point out a connection with another type of problem, actually we looked a couple of years ago to something called a Wigner crystal, which is something existing in higher dimension with Laetitia Couliandolo and Pierre Ledoussal. But look at the Hamiltonian we were examining. That's exactly the same. That's the pi square plus grad u square, so that's our free Tomonaga liquid Hamiltonian. And this is a cosine with a random phase here, u. Except here we are in 2D instead of being in 1D. Or we're, let's say, in arbitrary dimension. And what we found for this Hamiltonian is that if you do a quench of the chemical potential, so if you brutally change the chemical potential, what you find is that the density is showing non-ergodic behavior, is showing what is known as aging in a glass. So the observables depend on time and keep this dependence on time for a very long time. Whether this has anything to do with the many-body localization results or not, even that I'm not able to answer. So in other words, is glassy behavior connected to what people discuss in the framework of this many-body localization or not? That's an open question, and there are, again, some papers who try to address this question. Okay, so for this part, I would say there is a take-home message, which I think is undisputable, is that there is a remarkable interplay between localization and interactions. There is consequence and challenging both in what I would call equilibrium, which is the phase diagram I showed you. Let me call it localization of interacting particles to avoid having a conflict of designating two problems by the same name, and out of equilibrium, which is what is now known as many-body localization. And as I said, there are some elements which are understood, but there are many elements which are not understood. And what is more fun is that there is, again, experimental possibility to explore this phenomena. I have no time to show you this, but as you saw, the review paper is also signed by Emmanuel Bloch with an experimentalist. So they did actually this experiment that I showed you here. They prepared an initial state which was one particle every two sites, and they waited a certain amount of time to see if the imbalance was relaxing to zero or not relaxing to zero. Okay, so the conclusion, we need you, we need better tools, we need better concepts, we need better technology, whether numerical, analytical, intuitive, whatever you want to tackle this phenomenon, even if this is a 1D problem, strictly 1D problem. Okay, the second crash problem that I want to present is what is known as dimensional crossover. And there the question is very simple but very important, is how do you go from this peculiar physics of one dimension, which is the one of the Tomonaga-Lottinger liquids, this absence of quasi-particles and whatever. How do you go from this to the physics of 2D or 3D systems? And there is a very simple way you can do this. You take 1D chains, many 1D chains, and you start, for example, allowing tunneling between the chains. And if T-perp equals 0, I am in 1D. And if T-perp is different from 0, I will be here in this thing, I will be in 2D. For example, if T-perp equals T parallel, I have a perfect isotropic 2D system. So by controlling T-perp versus, let's say, T parallel, I can control whether I am in 1D and in 2D. So if this ratio is 0, I'm in 1D. If this ratio is 1, I have an isotropic 2D system or 3D system. And this is something which can be studied. You can also do it the opposite way. Say I have a 2D system, and then I put a periodic potential here. And if the periodic potential, so of course extending in this direction, if the periodic potential is very shallow, well, it's a 2D system with a small perturbation. But if the potential is super deep, if I put something like this, then I've sliced my system into 1D tubes, and these 1D tubes, they will behave as independent entities, and they will give me the 1D physics. Actually, that's how the people in cold atoms realize 1D tubes. They put a periodic potential, and they make it so large that there is no tunneling between one minimum to the other. So for bosons, I would say life is reasonably cool. And here I show you results that were obtained by Epeng Yao, who is here, and Lorenzo Pizzino, who is here, and published in an excellent review that I'm sure Jean-Sébastien can tell you more about, which is SciPost. And here I'm not joking. I think it's an excellent review, and I think it's a review which gives great service to the community. So here is the main result of the paper. Yeah, I have to be serious at least 10 seconds during 1 hour and a half, but these were the 10 seconds when I'm serious. Okay. I will. Tell me. Okay, so here is the phase diagram that is sort of obtained, and I won't discuss, this is obtained by Quantum Monte Carlo, that we get for bosons with the periodic potential. So that's exactly this problem. And this is the temperature. This is the strength of the potential. And ER is the recoil energy, so this is a sort of, let's say, scale of energy that is linked to the kinetic energy of the particle, essentially. So essentially, you see that if the temperature is super high, you get a thermal phase. It's totally boring. If you have a very weak potential and you lower the temperature, at some point the quantum effects take over below this green limit here, and then you get a 2D superfluid with Berezinski-Kostelis-Thouless transition and so on and so forth. But then if you increase the potential, this 2D superfluid starts to be sliced into tubes, but the tubes are still connected by a very good tunneling. So they are tubes, but they connect, their phases are coherent from one tube to the next. And then if you pass this line here, you go to essentially independent tubes because there are thermal excitation that take place before particles can have the time to tunnel from one tube to the next. So there you essentially get a collection of independent 1D tubes. And understanding how you do this, how you go from this phase to this phase to this phase, what are the consequences for the correlation functions, the single particle correlation function and so on. This is the large question of the dimensional crossover, and this is a very important question. I will not push too much on the bosons. I will just show you that there are unexpected consequences of the existence of this dimensional crossover. Here is a paper we just put on archive a couple of months ago, which is called Cooling Bosons by Dimensional Reduction. And this is done in collaboration with the experimental group of Hans Christoph Nagel in Innsbruck. So this is not just crazy theorists. You can cool, actually, by using this effect. If you want to know more, read the paper. Okay, but I will show you for fermions, because this is a crash section. So for bosons, we know we can compute, and the reason is for bosons, there are good algorithms who work in 2D. Quantum Monte Carlo is one of them, and it worked well. And people invented remarkable new algorithms, so-called worm algorithm, for example. This was invented by, in particular, Prokofiev and Svistunov in Amherst, which allow to really simulate big system of bosons, do low temperatures. So we are in good position. We have the power, we have the machinery. Now, let's talk about fermions. Fermions, sorry for the noise, but it was with the mouth. We don't have the power. But we have the problem. And the problem, here it is. These are these organic conductors that I showed you at the beginning of the talks. I told you, oh, they are made by stacks of molecules, and they are 1D. They are not 1D, they are quasi-1D, because the electrons can go from this one, they can hop to the next stack. So actually, if you look at these systems, there is a T parallel, which is about 3000 Kelvin, which, by the way, for an electronic system is low, but okay. This is 3000 K. A first T-perp, which is about 200 K, and then a last T-perp 2, let's say, which is about 20 K. So this compound, they go first, they are 2D, they are 1D. Then if you lower the temperature, they become 2D, and then they become 3D. Now you would say, how do I see that? Well, if you look at kinetic energy like this, minus T parallel, cosine K parallel, minus T perp, cosine K perp, and that you plot the Fermi surface. This is K parallel. This is K perp. You will have a warped Fermi surface whose warping is of the order of T perp. And now you easily understand that if my temperature is larger than the warping, I blur the Fermi surface, and I'm not very much able to decide whether it's 1D or 2D. So if the temperature is larger than T perp, I'm 1D. If the temperature is much smaller than T perp, well, I see that I have warping, so I see that this exists, so it will be 2D or 3D. So this compound, they undergo a dimensional crossover as you lower the temperature here. So at here, these are 1D compounds. When I go here, the metallic phase here is 2D. And when I go to the ordered phase here, the ordered phase are definitely in the 3D regime. These are spin piles, antiferromagnets. So essentially here, AF or spin density wave is magnetic phases. And this is a superconducting phase at a very low temperature. Nobody knows the mechanism or the reason why these compounds are superconducting. They are definitely non-BCS compounds. So, okay, just to tell that they are challenging. Actually, they were discovered, these are organic compounds, so this was the first time superconductivity was observed in an organic compound, and people thought that this could be a route for high TC superconductivity. Actually, okay, the TC is 2 Kelvin, but I think these compounds show many other interesting phenomena. So you have this compound, and they are having this dimensional crossover, and most likely all this beautiful physics here is resulting from this dimensional crossover. But how can you compute? Well, we don't know. We don't know. We know that there is probably a phase diagram like this. You see, when you see theorists putting dashed line, it means that they don't have the answer. It's a fake line. It's something which doesn't exist. So when you increase the T perp, you will go from a Mott insulator, and then because you increase the kinetic energy, the Mott gap should go down. You go through a Luttinger liquid regime here, but at low temperature, this will transform into a high dimensional metal, and you have certainly a phase diagram that is of this type, but with a gray zone here that we don't really know, and we don't really understand. The experiments seem to support this idea. These are measurements of the conductivity in these materials, and out of the temperature dependence of the conductivity, you can extract various characteristic scales, and you see that one of these scales is dropping down, one of these scales is going up, and this is at least consistent with the type of diagram that I showed you. But to be able to compute properly this diagram, there is no method. Quantum Monte Carlo fails miserably, sign problem. So the accuracy disappears exponentially with the lowering of the temperature. So you hit an exponential wall in the computational time that you would need to answer this question by Quantum Monte Carlo. DMRG is not efficient because I don't have to deal with one chain or two chains or maybe three chains, but I have to deal with an infinite number of chains. So entanglement is through the roof, and that's it, you're dead. So at the moment, there is no good method to deal with this. Even to compute transverse transport, for example, what is the conductivity perpendicular to the direction of the chain. So you can do some approximate theory saying, oh, well, if I am incoherent, I'm not doing real conductivity, I'm doing tunneling. If I am doing tunneling, I know how to deal with tunneling Hamiltonians, and what you find is, again, power laws of temperature with exponents that you can relate to the Luttinger liquid exponents in the system. So you would have a very different temperature dependence along the chain, which is metallic, from this one, which would be rather an insulating-like behavior, because you see that if the exponent is positive, then this would represent an insulator. Here is a measurement by the group of Martin Dressel of the conductivity along the three axes, A, B, and C. A is along the chain, B is the easiest direction perpendicular, and C is the hardest. And if you look, this is a logarithmic scale, you will see that the C conductivity, resistivity, is going up, while the B and A conductivity are going down. So definitely, this is not an isotropic metal. You have one direction which is resistive and two directions which are metallic. And then, haha, something happens here. And it becomes like the others. Dimensional crossover. Where the system realized, no, I'm not made of incoherent 1D chain. I'm made of 2D planes. And then if I'm made of 2D planes, this direction should be the same than these guys. And that's it. But how to compute this properly and so on is a very difficult question. Okay, let me skip this. So how do you attack such a problem? As I said, it's not because you cannot solve the problem that you cannot try and that you cannot publish paper on it. So, but you have to be aware that what you say is not the ultimate truth of the system. So we tried various methods, and so let me tell you our failures, if I could say, or attempts, and I'm very proud of these attempts, but they are attempts, and we still need more than an attempt. So this is something we did a long time ago with Silke Biermann, Antoine Georges, Sascha Lichtenstein, and more recently with Christophe Berthaud, which is to say, let's attack the problem by the so-called dynamical mean field theory, where you view the rest of the universe usually compared to one site, in our case compared to one chain, as a bath. So I replace all the other chain by a bath, and now I will say I have a single chain problem in which the particles can leave, go in the bath, come back, and this will modify the kinetic energy of the particles in the chain, and I have to determine this modification self-consistently, and out of this we could obtain results, like for example, how does the Fermi surface evolves as we increase, for example, the perpendicular coupling, and what we see is that there are pocket formations that occur first, and these pockets extend, and then they give you the extended Fermi surface that you would get. Here is the spectrum that you would see in photoemission. This pocket would look like arcs because they have a very asymmetric intensity. So again, it gives some answers. Some of these answers are very satisfactory. By the way, some of these arcs like this have been observed with high TC materials. Whether it's the same kind of thing due to pockets and people see only half of the pocket, or whether there are other explanations, that's something which is debated. But there are also other things that this theory doesn't give correctly when we compare to experiments in the organics. It's a mean field theory, and it makes a kind of average in the transverse direction, assuming that there is essentially an infinite number of chains which are coupled to a single one. So this is definitely not something that is well appropriate to going from 1D to 2D. One can try DMRG. So this is something we attempted with Adrien Cantillon, Michele Dolfi, and Matthias Treuer. And of course, we need to put a little bit the algorithms on steroids. But and so we essentially worked out at the time a parallelization of the DMRG codes, and this helps. So, for example, we could try to treat chains with nearest neighbor and on-site and nearest neighbor repulsion, and try to see whether such chain, when we transform a single chain to 2 chains, to 3 chains, to 4 chains, and so on, into a plane, still retain a spin gap, for example, which is something that you would get in the 1D problem. This becomes incredibly difficult, and beyond 8 chains, it becomes extremely difficult to go. So we could try to extrapolate from what we have for 2 chains, 4 chains, 6 chains, 8 chains, and decide whether or not we still have a spin gap, which would mean an unusual ground state for our 2D system, not just a stupid Fermi liquid. Okay. You can look at the paper. I think we believe at our results, but the extrapolations are really, really difficult. In the sense we are really extrapolating not to zero, but to a very small quantity. If you think about this in high TC, the Fermi energy is 10,000 Kelvin, 1 electron volt. The TC is 100K. So there is 2 orders of magnitude reduction. So in units of T, it would be 10 to the minus 2. So this is not abnormal what we have as order of magnitudes here, but it makes it extremely difficult to extract from a brute force DMRG trying to go from 1D to 2D by simply growing the number of chains that one can do. So we move to a sort of more civilized strategy, which is to say, let's do a couple of chains, but then we treat the rest by mean field. And so this is a work with a group of Adrien Cantillon, Gunnar Bollmann, Thomas Koller, also Lorenzo that you saw on the paper on the bosons, and also people from the Flatiron group who contributed to Monte Carlo, essentially part of the study. And this was led by Adrien Cantillon. And essentially with that we get better results, because of course we truncate the number of chains we can do, but we do mean field. And you know, you believe in mean field or you don't believe in mean field, and that's life. So that's where we are. I'm not trying to oversell you these results. I think they are great results, but I don't want to oversell them to you because there are good reason to say, oh, my approximation is better than your approximation. Yes?
But is this better than GMFT or?
Define better. Yes, because in the DMFT here, the solution of the 1D problem with the modified kinetic energy was done through Hirschfeld algorithm, which has a sign problem. So we had to take drastic measures to go to low temperature with this type of solution. It's probably now a little bit better because this was 2006. So now there are better solvers, but to the best of my knowledge, all the solvers have sign problem, which means that here, if you want to know what is happening to low temperature, you have to do something drastic. The drastic thing we did is to guess a form of the self-energy, which depended on 3 parameters, 3 numbers. And then we fitted these 3 numbers by the solution in imaginary time. And we can get, with this form of the self-energy and these 3 numbers, a perfect fit to all our Monte Carlo data at the temperatures we can reach, which doesn't tell you that if you go to lower temperature, you will not see deviations. But with the regime we could reach, this is as good as our Monte Carlo data. And then we can do the analytic continuation on the analytic form, which is much nicer. But this assumes we've gotten the right analytic form. And this assumes that at lower temperature, there are not deviations from the behavior we've seen. And that we cannot answer because we cannot go to lower temperatures using the Hirschfeld algorithm. So the advantage of the DMRG procedure is that the DMRG itself doesn't suffer from any sign problem. So we can function at t equals 0. And the solution of the many chains here, 3, for example, is perfect. There is no problem in, oh, it's tough. I mean, this is months of calculation, but this is perfect. There is no sign problem, no convergence. If Adrien tells me the results are converged, I close my eyes and I say they are converged because there is no reason why they shouldn't be converged. Now, the price we pay is that then, in order to decide how the coupling to this guy is there, that we treat in mean field. And when we do this, we do a truncation, we neglect some fluctuations. So the limitation is in this treatment. Now, if I tell you, for example, I have spin chains, And I do this. I have one single chain, and I treat the other ones in mean field. You would say it's not super. But now I tell you I take 3 chains, and now I treat those connections in mean field. Maybe you would say it's not super. But then I tell you I get 7 chains. 1, 2, 3, 6, 7. And I treat these connections in mean field. After a while, you would say it doesn't matter. It's just a kind of stupid boundary condition that you put. So certainly, if we go to 1001 chain, this method is excellent. The problem is that we can do 3, maybe 5. So, you know, again, you decide which one is the least worse. That's why I was saying define better. We get things which are in very good agreement with some analytical predictions that we could do with Lorenzo, for example, on the ratio between the gap and the TC, things like this, but there are also things which are clearly in the air. So if you find a better method, by all means, do it. Publish. And even if it's not perfect, publish. Okay, and let me finish with, now in the 15 minutes that I am left, with what I would call intermediate systems. Because there are a lot of systems where, in a way, you saw that what I would like to solve is not a 1D, is not a 2D, is not a 3D system, but is a system which I would say is an intermediate dimension. So it's a system which is in contact with a bath. And this can be a 1D chain in contact with another bath. This can be a particle in contact with a bath, and so on and so forth. And I will show you a couple of examples. Again, this is the crash section, where we try to study these systems. And there are some examples where we can do something, and there are others which are really tough nut to crack. And this is also something that is going well with an out-of-equilibrium session, because very often the coupling to the bath is doing something to your system which makes it not very much in equilibrium. I'm sure Tony will tell you more, for example, about the situation where you get one bath here, a little system here, another system here. These are called reservoirs, and you pass a current through the system. And you can even send microwaves here to make a time and space dependent potential, and this will change the transport of the system. So these intermediate systems are neither 1D, nor 2D, nor 3D. There can be a 1D system with a 3D bath. They can be a 0D system with a 1D bath. You can do all these things. So let me give you the simplest problem, which is one impurity coupled to a 1D bath. So p squared over 2m, that's my impurity. It's a free particle, and then it's a blue atom, let's say. And then I have H1D, which is, let's say, a bath of bosons. And then these ones interact, they are letting a liquid, they do whatever they want, it doesn't matter at that stage. And now I have a simple interaction between my impurity and the bath of bosons, which I can write in first quantization by saying it's V, the strength of the interaction. I don't want to call it U because I keep U for the interactions inside the bath. Times what? Times the density of the bath at the position X of the impurity. So this is the simplest problem that you can imagine. A free particle which is essentially interacting with a 1D bath, and then which is repelling, let's say, the particles in the 1D bath. And I don't see where Lorenzo is here, but he's here, voila. He's a specialist of this problem, so if you have tough questions, ask him. He's sweating on this problem. So in equilibrium physics, this problem is called a polaron, essentially. This is typically phonons, This is a free electron, and the electron distorts the lattice around it. And this is the so-called Feynman or Landau-Pekar polaron problem. And people have found perturbative, typically, ways of solving this problem. And this problem becomes not so simple if you start putting the impurity out of equilibrium, because essentially there is another phenomenon that occurs that people have called Anderson orthogonality catastrophe, which was a phenomenon identified by Anderson in the 70s, that if you take a 3D free Fermi gas, and if you change locally one potential, you would imagine, you know, I put a little potential at the center of a huge cube of free fermions, nothing happens. And what Anderson showed is that the ground state of this problem is orthogonal to the ground state of the free fermions without the potential. So not only you change something, but you make the two ground states totally orthogonal. So this was a big surprise at the time. Now it has a name. It's called Anderson orthogonality catastrophe. And this is something that will play a role in what we will discuss here. You could also view it as a quench. You heard about quenches, and I will tell you that I can do a local quench. You heard about global quenches, for example, in the talk of Jean-Sébastien. But imagine I have my blue atoms here, which will be the bath, and then everybody is happy, and suddenly I change one of the blue atom into a red atom. But it's the only one. So I've done something special here. I've quenched my problem by changing this guy into a red atom. And then I wait a little bit, and I want to know what is the chance I can find the red atom somewhere at time t. So I can measure the probability of finding my red atom. It's alone, so I cannot get wrong. I can find my red atom at point x after the time t. And this is a situation where I start from a case where I know that the red atom was at point 0, at time 0, because I created it here. So that's a local quench, what I would call a local quench. Instead of changing the potential on everybody, you just do something locally. Okay. If the atom cannot move, if the atom is infinitely massive, this is an old problem that was actually solved by Philippe Nozière in the 60s. It's called the X-ray edge problem. It's a beautiful problem in solid state that I won't comment, but essentially, if the particle doesn't move, this is the coupling of a system to a local potential that is varying, because you create the particle here, it interacts with the other, so it's like creating a local potential. And what you can show is that if you look at the Green's function of your impurity, you create it at point 0 times 0, it doesn't move, so it stays always at point 0. But at time t, this average is decaying as a power law of the time. So this is a spectacular result, which says that although your impurity doesn't move, the overlap of these two states here with the creation of the impurity decays, and decays as a power law of time, and this is a consequence of this Anderson orthogonality catastrophe. And then there was the mumbo-jumbo that when the particle moves, the recoil destroys this effect. Except it doesn't destroy it in 1D. So in 1D, you still have all these problems, and you have to deal with them. So how do you treat? Well, you can do bosonization, and you recognize the Hamiltonian. You recognize that U and K depend on interactions and the density has this shape, and whatever. And this is the density to which your local impurity will couple. It has correlation that decreases 1 over x squared. The other has the letting a liquid parameter in it. And this is a problem that we could solve with Misha Zvonarev and Vadim Sheyanov already some time ago. It's not a trivial problem, and you can solve it by, again, a combination of various methods. So gamma is the interaction with the impurity. So this is the strength of the interaction with the impurity. And you can solve it by various methods, which is either bosonization, a combination of bosonization and effective Hamiltonians, or better than that. So there are several attacks. What I will do, I will just show you what is the result for this quantity, which is the initial state where there are only up atoms. So these are the blue. The blue are called up here. Then I lower one of the blue, which becomes red. So this is clock going spin down at point 0 and time 0. And then I destroy it. So I measure it, if you want, at point x and time t. And then I'm back with only blue atoms. Okay? So this is a Green's function, which is just the spin flip, the single spin flip, that you would get in an otherwise polarized ground state of bosons. And this can be computed. So here is the Hamiltonian of the problem. This is my free particle. This is my red atom, which has kinetic energy. That you would say, what is this? Well, this is the Luttinger liquid Hamiltonian, which I've expressed not in terms of pi square plus grad phi square, but these are harmonic oscillators. So I wrote it in terms of the bosons of the harmonic oscillator. And this is the interaction between the impurity and the bath. And the bath is made of these bosons. So this is the expression of the density of the bath. So essentially, you see that you have a relatively an Hamiltonian which reminds you very much of the polaron Hamiltonian, where you could say, oh, these are phonons, and this is the electron-phonon coupling. So all these models are very close, but each one has its little peculiarity. Here is the answer, and this answer is essentially giving you this. So this is the origin. That's where you create the impurity. This is the time, and this is the position. If the impurity was moving ballistically, this is what you would have. Instead, this is where you find the impurity. This is already super small. You can check that the position here, the width here, x, is growing as the log of the time. So it's not even diffusive. Diffusive would be that x is growing as the square root of the time. It's subdiffusive. So this has very drastic consequence for the propagation of the impurity. So this is a case where the poor impurity doesn't know how to move in a bath of 1D particles when it starts to interact with them, and is heavily localized by this Anderson orthogonality catastrophe effect. So let me skip a little bit the details, but essentially this is the way the Green's function is behaving. Exponential of minus x squared divided by log of t. So you don't go far. Really, you don't go far. Okay. You can study a little bit more, but if you want to study more, you need more powerful technique, and one of the powerful technique here was the DMRG. And what the DMRG told us is that there are two regimes. There is a regime which is dominated by this infrared catastrophe, and there is another regime which is more complicated and which I will not discuss. And this also helped us to debug an analytic method which is called the link cluster expansion, because we could compare the prediction of this approximate method with the numerical result and check that it's giving accurate results. You can try to go to 2D again, because now this is something we reasonably understand in 1D for a single chain. But if you try to go to 2D, so this is the work that was done by Noshat Kamar in collaboration with Adrien Cantillon. And the way you try to go to 2D is, again, you try, for example, with a ladder. So you put your impurity not in a single chain, but in a ladder. And there, of course, your numerics become much worse. Much more difficult, and your analytics become much worse. So we could do two-leg ladders, but that's more or less it for the moment. And we don't know how to go beyond in this problem. So let me skip the details. Just to show you that this is again not just the crazy theorists. Here are experiments that were done in the group of Emmanuel Bloch. You take a system in an optical bath, you transform one of the particles into something else, and then you lower the barrier, and you do the quantum horse race. So this was done by, again, Stefan Kohr, Takeshi Fukuhara, and here Emmanuel, and Adrian was the theoretical support rock which helped doing this. So here is a measurement of the propagation of the impurity. At the origin, it's prepared on the central site. Then if you wait a little bit, sorry, here, you see that it has moved to a neighboring site. If you wait a little bit more, it has come back to the central site in part and moved further. And you see that this is a typical interference pattern because this is a quantum impurity. So it's not just propagating as a ballistic object. And if you wait more and so on, the histogram is the experiment, and the red curve is the Giamarchi procedure. So for this system, the numerical procedure is actually quite efficient. But these are systems which are only 10 sites long, and therefore it's a little bit difficult to really reach the regimes that I was discussing in the previous thing. Other examples, recently we have started to look at local baths. This is something done with Saptarshi Majumdar, Laura Foyni, and Alberto Rosso in LPTMS in Paris, where we take a spin chain, and on each side, so forget about the ondulation here, it's a flat spin chain, but it's just to show the rotation of the spin. But on each side, we attach a bath. So we have baths which are locally independent, but which vary, fluctuate in time, and which have a spectral density, which is given here by a certain omega, the frequency, at a certain power S. And the question is whether the presence of these baths, which are continuously measuring the spin by exchange with the spin here, are able to change the physics of the spin chain, which normally is dominant antiferromagnetic tendency, and give other type of orders. So this is something which is an open subject, and here again there is no perfect method, so we explore some of the possibilities. And in a similar way, together with Miguel Casalila and Cheno Wang in Donostia Center in Spain, we were wondering whether if we have a system in which there are particle loss, when there are particle loss, people write always this phenomenological equation, which is that the derivative of the number of particles is proportional to the losses times the density of particles, and that gives you a kind of exponentially decreasing solution. But actually, you can solve more microscopically this Hamiltonian, and we don't know how to do it fully, but we can do it by doing sort of second-order cumulant expansion, and we find strong deviations compared to this classical distribution. Voilà. I think I'll stop here. This was essentially a tour of one-dimensional physics. I think if there is one thing that you should retain is that there is the Tomonaga-Luttinger liquid theory, which provides a framework to study 1D physics, but more importantly, to go beyond 1D physics, to deal with out of equilibrium, disordered, coupled chains, you name it, and that's where the excitation is now. There are beautiful open problems out of equilibrium and so on, and essentially most of these problems require an interplay of analytical and numerical techniques, and more importantly, we need new ideas. We need new things, because I would say all the old tricks have been tried, and now it's really time to try some new tricks. And finally, there are absolutely remarkable realizations of this physics, both in condensed matter, and I tried to convince you that spin systems could be used even as quantum simulator, but certainly beautiful realization of TLLs, and cold atomic gases. And just before I conclude, I cannot resist to show you the image of the group. This is an already a little bit ancient photo. Find who has now a new position in Nice. I'm sure you recognize him. And there is also Lorenzo, who was not on this photo, but we should be, and we should take a new family photo pretty soon. We're also looking for postdocs, so by the way, if you're interested, don't hesitate. And on that, I stop, and I thank you for your attention.